Okay, so more examples. Let's do something like this. How about f of x equals e to the 2x? What's f prime? This function is e to the something, right? The derivative of e to the something is e to the something. Okay? This is, the derivative of e to the x is e to the x. I expect the derivative of e to the 2x to be e to the 2x. Okay? But 2x is changing at a different rate than x changes at. Right? So I have to multiply by that rate. Okay? The derivative of 2x is 2. That's 2 e to the 2x. That's it. If you wanted to, if it helps, and it may for some of us, right? You can split this up so that it's e to the u, right? And the derivative of that is e to the u times u prime. Right? The derivative of e to the u is e to the u, but then you have to multiply by the derivative of that exponent, the derivative of that inside function. And then you just have to plug in the appropriate values. U is 2x, u prime is 2, so that's e to the 2x times 2. It gets you to the same place. It's just that here you've already broken it up into an outside function and an inside function, right? An outside function, e to the u, and an inside function, 2x. Yes?
So I'm guessing we would do the right side when he just is on the right. That would be something we would save for more complicated ones.
I would sometimes use this just for like really complicated cases. But as you, almost all the time you can do the left one. Right? In fact, the more problems of these that you do, you're going to want to do more of the left and a lot less of the right. This is kind of complicated, always pulling these functions apart and then dealing with them separately and then gluing them back together. I don't want to have to do that all the time. I'd much rather just kind of like look at it in the situation that it's at, recognize that it's a composition of functions, and then have a run at it.
So I mean, actually finding e to the x is just like finding that, except it's just getting multiplied by 1, so we just assume.
Exactly, right? So this is, right, e to the x, right? Its derivative is e to the x, but then I multiply by the derivative of x, which is just 1. Okay? So it's really kind of what we've been doing all along. It's just that the derivative that we have been seeing change, right, x, the rate at which x changes with respect to x is just 1. But if that's not an x, right, e to the, 4x, right? Right? 4x is changing at a different rate than just plain old x was. It's changing at 4 times the rate. So we get 4e to the 4x. Questions here? All right, let's see another example.
Would that exponent just be 4, not 4x?
No. The function, the inside function, does not change.
The derivative of 4x, though?
Is 4, it's right here. The inside function does not change. Yeah. You are not going to be the only one that hits this speed bump. The derivative, right, of f of g of x is f prime of g of x times g prime. Right? This guy unchanged. Right? that complicated inside, right? That duck inside of the turkey that we are pretending is not there, right? That complicated center, we're just going to kind of ignore it to begin with, right? I'm pretending it's not there. And so when I take the derivative, that it's just going to kind of be left alone, right? I haven't done anything to it. It's only after I've kind of evaluated the function with everything put together that I say like, oh, well, really that 4x is more complicated than what I was giving it credit for before. Really that 4x is changing, and so I'm going to need to multiply by its rate of change. So that's where that'll come from. In general, and this may be where a lot of us go, the derivative of e to the something is e to the something times the derivative of that something. And this is just the chain rule put together with the fact that we know that e to the x's derivative is e to the x. Right? This is just kind of us merging those two rules. There's no real reason to memorize this fact, but some of you may find this easier if you just kind of have at it this way. So things like e to the 4x go to e to the 4x times 4, right? E to the square root of x will go to e to the square root of x times 1 over 2 root x. Right? It stays exactly the same, but then I multiply by the derivative of that exponent. E to the 1 minus x squared will go to e to the 1 minus x squared times negative 2x. Right? It stays exactly the same, but then I have to multiply by the derivative of the exponent. And that's just the chain rule in action, right? E to the something, its derivative is e to the something. But that something is not just a plain old x, it's more complicated than that. So using the chain rule, I multiply by the derivative of that something, that inside function. This only works with things that are base E, like this in general rule. But the chain rule works for all composite functions as long as I know the derivatives of the things that I'm putting together. Right? So for instance, we know, and we have not yet figured out exactly how this is put together, but we know that 2 to the x, its derivative is 2 to the x times some number. I don't know what that number is exactly, but I know that there's some magic number that will be true for. No, this is just the general rule for exponents. We did this thing where we had like the limit as h goes to 0 of a to the x plus h minus a to the x all over h, and we found that it was a to the x times the limit as h goes to 0 of a to the h minus 1 all over h. It's in our notes kind of from way back. This isn't super important. The thing is that I know that the derivative of a to the x, right, here it is by definition, and we wound up finding this. And this doesn't depend on x at all, so this is just some number, depends on a. For 2, let me tell you what that number is exactly. That number is about 0.69. Right? So I know that the derivative of 2 to the x is 2 to the x times 0.69. The reason that e is special is because the derivative of e to the x is e to the x times 1.
So you just punched 2 to the x in your calculator?
How
did you find that 0.69?
The way that I found it is because I can see the future of this class, right?
So
We
we don't have to do that yet.
don't have to do this, yes. We will find out where this 0.69 comes from. But right now, you could find that it was 0.69 by trying to find the limit as h goes to 0 of 2 to the h minus 1 divided by h. So you could start plugging in very small values of h into this expression and try to see where they wind up heading. And they wind up heading to something like 0.69, 3147118, et cetera, et cetera, et cetera. It's a non-rational number. It's not a fraction. It's this weird kind of pattern that doesn't repeat. So it's something weird, but it's specific to 2, right? And the magic thing about e is that the derivative of e to the x is e to the x times its magic number is 1. So that it's that number whose derivative is itself. The derivative of 3 to the x is going to be 3 to the x times some number a little bit bigger than 1. Right. All that to say this. If I had the derivative of 2 to the, say, 10x, I know that the derivative is going to be 2 to the 10x times 0.69, right? I'm going to take the derivative just like I normally would. I have 2 to the something, so the derivative is going to be 2 to the something times 0.69. 2 to the 10x, 2 to the 10x times 0.69. But this 10x is not just an x. It's a 10x. So I have to multiply by the derivative of that expression using the chain rule. So here's the chain rule in action on something else. This isn't about, because it's not really 0.69, it's a number that rounds to 0.69. So for other exponential functions, this chain rule will interact with them a little bit differently. But not super differently, right? You take the derivative like you normally would, leaving that inside function where it is. 2 to the 10x, 2 to the 10x times 0.69. Because 2 to the x was 2 to the x times 0.69. Here the difference is that this is an x, this is a 10x. So the difference is this is an x, this is a 10x. I'll leave it exactly the same. But then I multiply by the derivative of that thing that's not what it should be. That's more complicated than I want it to be. I multiply by the 10 at the end. So here's how it will be playing out with exponential functions as we see how those work out in the future. Maybe by the end of the day, since we're interested. Once we have mastered the chain rule here, I'll be able to kind of figure out where the 0.69 comes from more exactly. But I gotta have the chain rule first. That's the missing piece. So exponential functions we may see, or we may also see things like this: x squared plus 1 raised to the 10th power. So what's y prime?
10 times the x squared plus 1 times 2x.
Right? So I have something to the 10th power. So its derivative is 10 times that something to the 9th power. But I'm not done yet, right? Some of you are going to get this bit and forget the next bit, right? I have something to the 10th. So the way that I differentiate those types of things is I bring the power down and I subtract by 1. Notice that the inside has stayed exactly the same. Right? But this inside, this x squared plus 1, is a lot different than just a regular old x. And so I have to multiply by its derivative at the end. This is the chain rule. It tells you, take the derivative like you normally would, but then multiply by the derivative of that inside function. Yes?
And can you multiply that 2x to the 10, or would you have to multiply it to everything, or should we just leave it where it's at, just like that?
Are you saying like multiply this 2x back into this expression?
Is there another step after that?
I have 10 times 2x. Those seem like they would be easy to combine. Moving this inside of this exponent seems harder. Yeah, so I might say 20x, x squared plus 1 to the 9th. But these aren't, they aren't raised to the same power, so they can't be combined in a meaningful way. This would be the simplified, this is as simplified as it gets. 20x times the quantity x squared plus 1 to the 9th. But these are 10 times 2 times x are easy to do. But 20x times x squared plus 1 to the 9th, this 9th exponent happens first. Right? And so I can't meaningfully combine this in here just yet. Not in a nice way. If they were both raised to the same power, then maybe I could, right? So for instance, if I had e to the x squared and x squared, these are the same power, so I could make that x e to the x squared. Okay? But these aren't the same power, so I can't go ahead and do that multiplication. Now, just as a purely academic exercise, nobody has to pay attention to this if they don't want to. If you really were desperate to mush those things together, okay? Even though one is peanut butter and the other one is like anchovies, right? Those do not taste like two things that really need to be mushed together, and these don't really need to be mushed together. But, you know, if you had a hankering, then you might try to engineer a situation like this. So you might do something like the 9th root of 20x raised to the 9th power. That way you haven't changed this expression, but now it has a 9th power to it. And now you could combine these because they're both 9th powers. You would just have the 20th root of the 9th root of 20 and the 9th root of x times x squared plus 1, and all of that would be the 9th power. Okay? So see, it's not friendly. But if I really had to mush them together, I might try to come up with something, right? If I were desperate for peanut butter and anchovies, this could happen. But really, right, this is where we are. Right? Here's the derivative of that expression. In general, right, I might try to apply the chain rule to this power rule that I'm really friendly with. Right? So if I have f of x raised to some power, its derivative, the power comes down, the inside function will stay exactly the same, and I will reduce the power by 1. Right? Just like I normally would. But then I'm going to multiply by the derivative of that inside function. So here's the general power rule. So if you're all about memorizing facts, here's something that you can memorize. But again, there is no reason to memorize this. You are much better kind of having an understanding of what the chain rule does and then just applying the chain rule to this situation like you do all situations. But especially this rule, it comes up often enough that this is what we do. So here, x squared plus 1 to the 10th, right? The power comes down, you reduce the power by 1, and then you multiply by the derivative of the inside function. And here we are. Not too bad.